All right, minions. As promised, we're back. Section 2 of the soils. This is the only chapter, for some odd reason, that has multiple sections. But without further ado, I'll get going. I know that this is not the most riveting stuff in the world, but here we go.
Welcome to Chapter 1, Section 2 of the Ohio Certified Nursery Technician Training Manual, developed by the Ohio Nursery and Landscape Association. In this chapter, we will learn about soil basics. To understand pH values, we will need to dive back into chemistry and take a second look at water. The water molecule plays a critical role in soil pH. pH stands for potential hydrogen, and it is driven by the self-ionization of water. Occasionally, a water molecule will simply fall apart, producing two ions, a positively charged hydrogen ion, a cation, and a negatively charged hydroxyl ion, an anion. pH is the relative amount of hydrogen ions in the soil solution. The soil solution is the hydrogen that is floating around within the water in the soil, and they are not attached to soil particles. Looking again at the pH scale, we see the acidity is based on the number of hydrogen ions. It is a logarithmic scale, meaning that with each step increase in acidity, the number of hydrogen ions have increased tenfold. Hydrogen and hydroxyl ions floating within the soil drive soil chemical reactions. So, soil pH has a direct impact on the availability of soil nutrients to plants. As soil pH changes, the nutrients leave the soil and become tied up through chemical reactions. This chemical reaction tie-up makes them unavailable to plants. This can lead to nutrient deficiency symptoms in plants, like these iron deficiency symptoms on oak, or these manganese deficiency symptoms on red maple. How do you raise soil pH? First, you must get rid of hydrogen ions that are floating within the soil solution. To do so, add calcium carbonate, commonly called lime. The lime molecule has one calcium atom, Ca, one carbon atom, C, and three oxygen atoms, O. hydrogen ions are found in two places in the soil: free floating within the soil solution and attached to clay particles. Lime first affects the hydrogen ions in the soil solution. Each lime molecule gets rid of two hydrogen ions. As a result, pH rises, which means the soil becomes more alkaline. It is now less acidic because there are fewer hydrogen ions in the soil solution. But what about the hydrogen ions that are attached to the clay particles? They can detach from the clay particles and enter the soil solution. More hydrogen ions in the soil solution means more acidity, so the pH drops. Here are some important soil chemistry terms. Reserve acidity is directly related to the number of hydrogen ions attached to the clay particle. It's the number of hydrogen ions held in reserve. Remember, these ions do not directly affect soil pH. Would soil with clay particles that look like this have a high or low reserve acidity? It would have a high reserve acidity due to the high amount of hydrogen. A buffer resists a change in pH, and a high buffering capacity means a high ability to resist a change in pH. A soil with a high reserve acidity also has a high buffering capacity. All of the hydrogen ions held in reserve on the clay particle means it takes more lime to change the soil pH. These two soils illustrate buffering capacity. Soil A would require less lime since it has few hydrogen ions held in reserve, compared to soil B, which has a large number of hydrogen ions held in reserve. Soil B has a high buffering capacity. So, what does buffering mean to you? Let's examine a case study of two soils and their lime requirements. Soil A has a pH of 5.0, and we want to raise the pH to 6.3. To do this, the Soil Test Lab recommends we add 10 pounds of lime per 1,000 square feet. Soil B also has a pH of 5.0, and we also want to raise its pH to 6.3. To do this, Soil Testing Lab recommends adding 20 pounds of lime per 1,000 square feet of soil. Why does it take different amounts of lime for the two soils if they have the same starting pH and the same desired pH? As you can see, the two soils have different reserve acidities, so they have different buffering capacities. This is why we cannot develop standard lime recommendations that will raise pH levels from one pH to the next. Soil testing labs measure both the soil pH based on the hydrogen ions floating around in the soil and the number of hydrogen ions attached to the clay particles which form the reserve acidity. They use both pieces of information to develop lime recommendations. Calcium and magnesium are two additional important nutrients measured by soil tests. If a soil test indicates a lime deficiency, calcium sulfate, also known as gypsum, can be used to correct the lime deficiency without changing the soil's pH. Likewise, if a test shows the soil is deficient in magnesium, then magnesium sulfate, known as Epsom salt, can be used to correct the magnesium level without affecting the soil pH. Fortunately, magnesium and lime deficiencies are seldom found in Ohio soils. However, such conditions could still exist in manufactured soils. We will now return to the physical properties of soil and discuss how to rebuild damaged soils. We are not literally rebuilding soil. However, to understand how to help damaged soils recover, it's important to understand how soils are built. Building soils is similar to building a house, and soil texture is like the basic construction materials. Sand, silt, and clay are like the nails, lumber, and cement that are eventually put together to form a recognizable structure. A pile of sand, silt, and clay is no more recognizable or functional as soil as a pile of construction materials is functional as a home. Soil consistency is like the house's framework. It provides some indication of what the final home will look like, but is not the final product. Soil structure is the soil's final form. Consistency describes the general organization of the soil. It is often a temporary condition and is described using terms such as loose, friable, firm, and extremely firm. You can change the soil consistency using a plow or a rototiller. Soil structure is the final form of the soil. It is intended to be long-lasting but can be destroyed by plowing, rototilling, or from soil damage during construction. Here is a graphic representation of soils with different structures. Again, we cannot produce these structured soils with a rototiller, but we could destroy them. Once soil structure is destroyed, it cannot be recreated in its original form. However, this usually refers to the original structure that may have required hundreds or even thousands of years to create. The good news is that good soil structure can be recovered if you understand how the biological properties of soil affect the recovery. Once again, do not forget that the different properties of the soil interact. Next, we will discuss soil's biological properties. Forest soils are the best type of soil and is made of many components that create healthy landscapes. A cup of forest soil holds a tremendous quantity of life. This graphic depicts a soil snapshot showing the soil particles and the tiny micropores that exist between the particles. However, soil contains more than just particles. It also contains living organisms like bacteria and fungi. These living organisms exude matter, usually in the form of waste products, that coats the surface of the particles. This exuded waste matter is called microbial glue because it makes the particles stick together. However, this glue is not that strong, and the particles can easily be broken apart. This image depicts a soil aggregate. We improve soil structure by applying an aggregation of knowledge. This graphic depicts soil with structure. It has particles clumped into individual soil aggregates, and between the aggregates are large spaces known as macropores. Macropores are very important to root penetration, water drainage, and oxygen retention. Micropores exist within the soil aggregates and between the individual particles. They are far less important to plant health than the macropores. Soil with good structure has a higher ratio of macropores to micropores than soil with poor structure. These soils are exactly the same. The only difference is that the soil on the right was tilled annually for 5 years, while the soil on the left remained unplowed for 43 years. You can clearly see the aggregates in the soil on the left. In the soil on the right, the aggregates were destroyed and not given time to reform. Tilling can improve soil consistency, but it destroys soil structure. This graphic depicts the numerous benefits of adding organic matter to the soil. The increase in soil aggregation leads to improved pore structure, meaning more macropores and improved soil tilth. Tilth is a soil structure term that indicates the soil has biologically produced aggregates. By adding organic matter, you will fire the biological engine that improves soil structure. In result, you can recover damaged soil structure. A word of caution regarding organics. Not all organic matter is the same. This table shows different forms of organic matter and their carbon to nitrogen ratios. Microorganisms require nitrogen to utilize carbon. When the carbon to nitrogen ratio is above around 30:1, the microorganisms will take nitrogen from the soil at the expense of plants. You can see nitrogen deficiency symptoms in plants. Properly produced compost has a carbon to nitrogen ratio of around 15:1, and any of the organic sources above the red line can be dropped below the red line by composting. Organic mulches also serve as a source of organic matter that can support the development of aggregated soil. Now, let's revisit soil compaction. This graphic depicts what happens when aggregated soils are compacted. The aggregates are broken apart, which results in the loss of macropores, but an increase in micropores. Compacted soils have a larger amount of soil particles per volume compared to non-compacted soils. In other words, a given volume of compacted soil weighs more than the same volume of non-compacted soil. This leads us to bulk density, which is a way to measure and quantify soil compaction. We start with a known volume of soil. In this case, it is a box of soil with a volume of 1 cubic centimeter. The box weighs 1.33 grams. This shows the formula for calculating bulk density. Divide the weight of the soil by the volume of the soil. The bulk density is 1.33 grams per cubic centimeter. This graphic represents real data gathered on a farm near Wilmington, Ohio. The bulk densities for soil at different depths were determined, and the results clearly show the soil compaction zone produced by years of annual plowing. From what we've learned of soil compaction, we can now discuss a way to deal with it. Listed here are the steps to treating soil compaction. First, if possible, it is simply best to prevent the problem. A protected root zone, or PRZ, is one way to avoid causing harmful compaction around trees during construction. A PRZ is calculated by determining the radius of the drip line and multiplying that number by 1.5, then multiplying the result by 2. In this example, the drip line radius is 10 feet. By doing the math, we find that the PRZ is 30 feet. The PRZ should be clearly marked to keep equipment off of the zone. The next step is to determine if you're dealing with true soil compaction or a soil problem that mimics compaction. As noted at the beginning of this presentation, there are several problems, including heavy clay soil and topsoil removal, that mimic compaction. If compaction or another problem exists, the next step is to take action. Core aeration involves drilling holes and backfilling with loose topsoil that is mixed with organic matter. The exact ration depends on the texture of the surrounding existing soil. Adding topsoil should be done cautiously. First, make sure the topsoil is indeed better than the existing soil. Second, always mix the new soil with the underlying existing soil to create a transition zone. Adding topsoil may be the best option if the topsoil has been removed and sold. The following slides will illustrate subsoilers and an air spade or knife. Subsoilers attach to a tractor and are pulled through the soil at depths below plow compaction zones, or false clay layer zones created by eluviation. Obviously, using subsoilers on home landscapes is problematic, given the risk for destroying underground wires and utility lines. An air spade or air knife is a device that uses high-speed bursts of air to blast soil away from roots. University studies have shown these devices do not cause root injury. These images show the tip of an air knife and an air knife in action. The device requires an air compressor and proper personal protective equipment for the operator. The air spade is being used to expose roots to correct root problems. This image shows the roots exposed by the air spade. The device allows the operator to correct soil compaction or to replace the existing soil with better soil. An air spade or air knife may also be used at planting to produce radial trenching. The radial trenches are backfilled with a mixture of existing soil and organic matter. Research has shown that trenches produce pathways for root growth and may help when planting in compacted soils or soils that are high in clay. This is an image of a high-capacity air knife being used to produce radial trenches around existing established trees. The tree's roots have been exposed by the air knife. Also, notice that the sod has been cut and rolled to be redistributed. This reduces the impact on the appearance of the landscape. The trenches are refilled with a mixture of existing topsoil and organic matter. This series of images shows an air knife being used to fracture the soil, which loosens the soil and allows deeper penetration of oxygen. It also helps with water infiltration and drainage on compacted soils. Watch the depth of the air knife as the slides progress. The holes are not very noticeable and could remain open or backfilled with organic matter. Correcting a soil compaction problem requires a mixture of patience and a long-term recovery plan. Compacted urban soils will be improved over time with the annual addition of organic matter to support microbial activity. Remember, this will eventually lead to the formation of aggregated soil. However, it will not happen overnight, so patience is required. It will require several years for improvements in soil structure to occur. We've discussed many factors of soil and its formation, including soil's physical properties, chemical properties, and biological properties. Listed here are just a few concepts we covered in this chapter. Soil is the foundation element of the green industry, and understanding its structure, texture, and nutrients will improve your success in the landscape.
All right, kiddos, that was the second one. I hope it didn't put you to sleep too much. So like I said, now you should have the information along with the reading to finish the assessment, which is due next Wednesday, which is, if I pull up my calendar here, a week from today, which is the 25th. All right. I hope you guys are good. Have a good one, and keep looking at your email for upcoming stuff. Okay, later on, kiddos.